Hi! In this video, I'll be ending the journey of cardinality with more properties they can do with cardinality, and this will be the last video for discrete mathematics. I hope you have enjoyed the series, and let's start. So in the previous video, we have proven things when sets are countable in nature, such as the natural numbers, integers, and even the set of rational numbers. But we have also proven why the real numbers is uncountable, and so this gives us a way to say that n is not equinumerous to r, but we want to know who is bigger, and obviously r is bigger than n because it is quite intuitive. But what do we mean when we say someone is bigger than the other? Well, it means that there exists you want to say that a is less than b, it means that there exists an injective function from a to b, and it's strictly less than if a is less than b and a is not equinumerous to b. So you do know that a being less than b means there exists a injective map f, and then maybe you want to prove this is surjective, but that is not good enough because you want to prove that all maps are not bijective, meaning even if you prove f is not surjective, it does not prove that there does not exist a bijective map. And so you actually need to prove it for a general map that none of them can be bijection between a and b when you write this type of statements. And then you also need to form one of those maps must be injective. And so this gives us a way to compare when two sets, who is bigger than who in set theory. And then we have of course certain properties. We can just say that a is of course less than or equals to a less than or equals to b, and b less than or equals to c will mean a is less than or equals to c. So this is the reflexive property and this is the transitive. You can see a being less than or equals to b does not mean b is less than or equals to a, so of course it is not symmetric. But there's this thing about comparability or skewed symmetricness where a less than or equals to b and b less than or equals to a will imply that a equals to b. So for any set a and b, either a is less than or equals to b or b is less than or equals to a. And this requires the axiom of choice to be proven, and so we'll not dive into that because it's a bit too advanced for this basic tutorials. But just know that it requires the axiom of choice, and it is true that you can, for any two sets, you can always compare them. And then we can also, instead of finding an injective function from a to b to prove why a is less than b, we can see this as b being greater than a, and so we actually can just find a surjective function from b to a. And this proposition that there exists an injective function resulting in a surjective function and vice versa requires the axiom of choice as well, and so we shall not dive into that again. But with this, it proves that if a is countable, it means that there exists a bijection from a to a surjective function from n to a, and so you can say that a is less than or equals to n, and this now is a more shortened version of the criterion for countability, if you recall. And then similarly for finite, it means it cannot be a bijection of n, means a must be strictly less than n. This whole is consistent with our intuition that any finite set will be less than an infinite set. And if b is infinite and b is strictly less than n, then b less than or equals to n, then b must be equinumerous to n. And so you can say that n is the smallest infinite set in that case. And so by taking the contrapositive of this and using this result, and then we can say that for any infinite set, it will be larger or equals to n. And so n in this case is still the smallest infinite set. So this follows all from the criterion for countability and the criterion for infiniteness. And so you can just do it yourself to prove these statements, but it should be fairly simple. And so we'll not go into it. But we just want to have an idea of saying that n is actually the smallest infinite set. And now we'll go into some theorems that are very much more interesting. And one of them is Kentos Theorem. So Kentos did a lot of things in set theory and cardinality studies. And so he has actually proven that no set is equinumerous to its power set. Meaning there does not exist a set that has the same cardinality as its power set. Meaning, for all sets, A is not equinumerous to the power set of A. So let's assume that A is equinumerous to the power set of A. Meaning there exists a bijective function from A to the power set. And then we know that for any A, fx must then be an element of PA. This means that fx is a subset of A. And so you can ask the question that B equals to the set of elements in A, but not an element in fx. So you can just take the elements in A that's not within fx. And this being a subset of A would mean there's an element of the power set of A, and hence there exists a small a in A such that B equals to FA. So B now equals to this function FA. And now you just need to ask the question, if A is in B, that means A must fulfill this criterion, so A cannot be an element of FA. And so, but FA is B, so A is not in B. And this leads to a contradiction. Similarly, if A is not an element of B, it means A is an element of FA, which equals to B, so again a contradiction. Hence, A cannot be equinumerous to any of its power sets. And we can obviously see there's an injection from A to the power set. Hence, A is strictly less than the power set. And so this gives us the corollary that there is no larger set of all sets. And you can actually see from the proof here that this is like a similar proof to when we prove why there's no set of all sets. And so there is also no largest set in the case, because you can just always take the power set and extend it to infinity. And so n being strictly less than Pn being strictly less than the power set of Pn goes on. And so you can just keep taking the power set, and so there is no set that is the largest. And then there is also a fairly intuitive but requires a harder time to prove, and you can read the textbook on the proof, which takes 4 pages by the way. Which is the Cantor-Schroeder-Bernstein theorem, or the Cantor-Bernstein-Schroeder theorem, where it says that if A is less than B and B is less than A, then A must equals to B. Less than or equals . So this is a very interesting and not so simple to prove result, because it actually doesn't say how F and G are related. Because you know that F is injective and you know there's a injective G, but it does not say that F and G must be inverses of each other. And so, to come up with a new function that is a bijection actually requires some skill. But the proof of this, you can read in the textbook, and because of this, you have now reduced a problem of finding a bijective function, which could be hard because surjection is tough, to identify injective functions which are easier to prove. And then this actually proves why the real number is equinumerous to the powers of n. Again, you can read the proof in the textbook. But you know that this is strictly larger than n, and so this proves that the real numbers is strictly greater than the natural numbers. But this imposes a question, and it's a very intricate question and a very nice question to think about, whether there is any set in between n and the power set of n. Since you already know p is less than n, strictly less than, is there any set in between them? And this is actually the continuum hypothesis, known as the continuum hypothesis, which says that there does not exist a set in between them. But it is not proven to be true, and it also cannot be proven to be false. And so it can be taken either way, and it will still be consistent with set theory. And that's the most interesting part about mathematics. So continuum hypothesis says there is no set in between them, but you cannot prove this proposition, but you cannot disprove it as well. And so you can think of it as a predicate, and when you want it to be true, you just assume it to be true, and when you want it to be false, you just assume it to be false. But you cannot assume it to be both at the same time in the same proof, or that's a contradiction. And so the continuum hypothesis is a fairly interesting result that you can read more about it, and it just says that there could be a set in between them, or it could not be a set in between them, and you want it to be true when you like it to be true. And so this ends the study of cardinality for us. I've also come to the last chapter of discrete math, where I put in together the uses of functions and build upon logic to get set theory, to get functions, to get relations, to get now cardinality, the study of cardinality. If you really like discrete math, you can consider computer science. And I've come to the end of what I wanted to teach in these basic tutorials. Hope you have enjoyed it, and feel free to like, share, and subscribe. And I'll catch you in other videos that I'll be considering doing, such as calculus. Thank you for listening.